Section 12.4 The Photoelectric Effect. Einstein designed the photoelectric experiment, proposed the concept of photons, and won Nobel Prize. So now let's look at this experiment. We have a piece of metal. We have incident light. The electrons on the surface of the metal absorb the photon energy and get ejected. The ejected electrons can be detected here. We measure the electric current and voltage. So the electrons will flow back to the metal and then get ejected again. We form an electric current loop. If somehow we can measure the kinetic energy of the ejected electrons as well and plot that against the frequency of the photons or the frequency of the light, we'll get a linear relationship. If you measure the slope, it's the Planck constant, 6.626 times 10 to the power of negative 34 joule per hertz. Over here, we can tell we need a minimum frequency, around 5 times 10 to the power 14 hertz to eject an electron. Now let's look at a simulation here showing the same experiment. But in this simulation, we can try different intensities, frequencies, and different metals. Unfortunately, I was not able to open this in Firefox. You are looking at Microsoft Edge. Now we have a piece of metal here. Incident light. What's the metal? The metal is sodium. And what's the wavelength? It's 100 nanometers. What's the intensity? It's 9% of the maximum intensity of this lamp. Alright, so I'm going to adjust the intensity. Now you have more electrons ejected from the metal. Lower intensity so that we can see the electrons being ejected one by one. Now I'm going to adjust the wavelengths. I will increase the wavelengths. That means I will decrease the frequency. What's going to happen? I can still eject electrons, but they are moving more slowly. How about 364? Again, the electrons are moving more slowly. Even slower. What if I'm using infrared? No electrons can be ejected from this sodium plate. The infrared light has a frequency that's too low to eject the electron. We can find the minimum frequency by adjusting the wavelengths. Maybe 530 nanometers, maybe 535. Let's try 535. Electrons are still being ejected, but really slowly. So let's try 550. 550 is not going to work. 545. It's not working, so we need to further increase the frequency. 540. Maybe 538. Okay, so we get the longest wavelength of the light that can be used to eject electron from sodium. That means the electrons need this amount of energy to overcome the attraction from the metal plate. Or more precisely, the electrons need this amount of energy to overcome the attraction from the sodium nuclei. Alright? Other electrons are pushing the electron away from the metal plate, but the sodium nuclei are attracting those electrons. Overall, the attraction is the predominant force. So that's why we need external energy to eject electron. 538. Now let's change sodium to platinum. Nothing is going to happen. No electrons will be ejected from platinum, because for platinum you need a higher frequency. So just picture this. It's easier to eject an electron from a sodium atom. It's more difficult to eject an electron from a platinum atom. You learn that in general chemistry. So similarly, when we have the solid state of sodium and platinum, we also observe that it's more difficult to eject an electron from bulk platinum than bulk sodium. So what's the minimum frequency or maximum wavelength for ejecting electron from platinum? I don't know. 317, it's not working. 246, it's not working. 110, it's not working. Oh, it's working. So let's try a bit longer wavelengths. 196, and let's increase the intensity so that we'll have more electrons being ejected. 196 is roughly the longest wavelength of the light, or the lowest frequency of the light that can eject electron from platinum. Alright, let's get back to this document here. We'll define the work function. The work function is the minimum energy needed to remove an electron from a solid. So if I ask you to calculate the work function for platinum, you go back to the simulation, you use this wavelength, 196 nanometers, and you use hc over lambda, plug in the values of h, the Planck constant, c, the speed of light, and lambda, the wavelengths here. You will be able to get the wave function for platinum. It's much higher than the work function of sodium, because you need, I think, a much lower frequency to eject a sodium. Now let's imagine an electron absorbs a photon and gets enough energy to be ejected. Well, it only needs the same amount of energy as the work function to be ejected. Alright? What if the photon energy is greater than the work function, and then this electron gets some kinetic energy? The higher the energy of the photon, the higher the kinetic energy of the ejected electrons. So we can predict the kinetic energy of the electrons is equal to h nu minus the work function. So if you plot kinetic energy versus nu, you will get a slope. The slope is going to be h, the Planck constant. And this is going to be the y-intercept, negative work function. So if you extend this line, you will get over here the work function, negative work function. If you extend the red straight line all the way to the y-axis, you will get the y-intercept. The y-intercept is negative work function. What about this x-intercept? That's the minimum frequency of the photon. that can eject electron.